Hello everybody. In this video, we will be going through question 16 through 20 of the SMO Junior 2020. Appropriately, the number 2020 appears a couple of times in question 16. It asks us to find the value of 2020 cubed minus 9 times 2020 times 2017 minus 2017 cubed. Firstly, we probably don't want to calculate this by hand, although let's admit it, if we were to spend 10 to 15 minutes on this calculation, we certainly can get it right, and perhaps it could be done in 5 minutes if your calculation skills are pretty good. But there are certainly better methods to approach such problems, and usually they come from some algebraic manipulation that has been obfuscated by using the year number, which in this case was 2020. So in order to get rid of this obfuscation, let's use a substitution and let x equals to 2020. Now you could also choose to let x be 2017. I'm just using 2020 since that was the year when this was set. So if we let x equals to 2020, the idea is that you can rewrite the entire expression in terms of x. 2020, you replace it by x. And 2017, don't leave it as it is, write it as x minus 3. So we have x cubed minus 9x times x minus 3 minus x minus 3 cubed. Now is anyone's guess whether this will simplify completely or leave us with something like x plus 10 or leave us with something like just 2020? I can't tell. But I can see that x cubed is already going to cancel out because the final expansion also contains an x cubed. And that's usually a good thing to notice. When you do a substitution, does the worst part of it cancel off? If the worst part cancels off, you're probably doing better than whenever you started. So x cubed, and we expand the second term, would be minus 9x squared plus 27x. Now we need to know the expansion of the cube, and this is x cubed minus 3x squared times 3 plus 3x times 3 squared minus 3 cubed. So this is just the usual expansion. If we simplify this, it would be x cubed minus 9x squared plus 27x minus 27. You realize now that this is literally repeated here and here exactly the same. So we could expand it out, or we could just realize that the only difference is that this is the same number minus 27, so therefore the difference must be 27. Now there are a couple of other ways we could have done the manipulation. For example, we could have used the difference of cube factorization for x cubed minus x minus 3 cubed. Or we could also have substituted x equals to 2017, for instance. Regardless, what we expect is that it is going to simplify a lot, and in this case it simplified to the extent where it was independent of x. Which means that 10 years from now, if someone were to substitute x equals to 2030 back into here, we could get another question with the same answer again. Next, question 17 is a geometry problem. It is really quite a simple figure. There is a rectangle. You have 2 points E and F on BC and CD, and then the area AEF is 2037, with some other ratio of areas also being given to us. So let's write down 2037 here. And it tells us that AECF is 2 times of ABE, which is 3 times of ADF. Now I like to use this kind of equalities where you have more than 2 things being equated and write it using a ratio. So what we can write is that AECF is to ABE is to ADF. Here it is times 1, and then times 2, and then times 3. So we can write it as 1 over 1 is to 1 over 2 is to 1 over 3. Because 1 times 1, half times 2, and 1/3 times 3 all give you 1. So this is a way that we can convert it straight into a ratio. And in order to get it to integers, I'll multiply everything by 6. So 6 is to 3 is to 2. Now, you notice that AECF, ABE, and ADF collectively form the whole rectangle. So that means that we can see that the rectangle is split in the ratio 6 is to 3 is to 2, and the total would be 11. So what is the use of this? Because we know what the whole rectangle area is, and a couple of these, ABE and ADF, are triangles, we can use that to determine how DF and BE actually are compared to the side lengths BC and CD. In other words, where are E and F on those sides? Now, ADF is 2 over 11 of the rectangle. It means that DF is 4 over 11 of CD. Now, if you're wondering how does this happen, one way to see it is using the area formula half base times height. Another way to see this is to temporarily draw in another line. So if ADF is 2 over 11, then this rectangle is 4 over 11, and that means that FD is 4 over 11 of the whole side length. Now, of course, it doesn't really look like this is 4 over 11, and that's a very useful reminder that our diagrams are often not to scale. In this instance, it is most certainly not to scale, because what we have just determined is that DF is 4 over 11 of CD. In other words, it is split in the ratio 4 is to 7, which is not how it appears initially. Well, similarly, since ABE is 3 over 11 of the rectangle, we can say that BE is 6 over 11 of BC. And so this is split in the ratio 6 is to 5. I guess this is a little bit more believable than the previous ratio. Now this is more or less all we need, because with these ratios here, we can find how AEF is as a fraction of the whole rectangle. Because CFE is going to be half times 7 over 11 times 5 over 11 of the rectangle, and this is 35 over 242. Once again, if you're wondering where did this come from, we could just have completed this rectangle, and this rectangle would be clearly 7 over 11 in terms of height and 5 over 11 in terms of length as compared to the whole rectangle ABCD. Since it is a triangle, that's where we get half. So this is 2 over 11, this is 3 over 11, and this is 35 over 242. With this information, it is pretty easy to get the remaining area in terms of a fraction of rectangle ABCD. Because AECF is 6 over 11, so 6 over 11 minus 35 over 242, which is a little bit annoying, but it is equal to 97 over 242 of the rectangle. This is equal to 2037. So we can breathe a huge sigh of relief if we divide 2037 by 97 and it is an integer, which thankfully it is. 2037 divided by 97 is just 21. So therefore, our area is 242 over 97 times 2037, and this would be 242 times 21. One more calculation to do, but once you're done, it gives you 5082. This is not very difficult, but it is admittedly a little bit tedious in terms of the computation at the end. Moving to question 18, we have got another geometry question and another large side length 64. E is a midpoint of AB, F is a midpoint of EC, G is a midpoint of FD. And we are asked to find the area enclosed by AEFG. We certainly have to make the most of the midpoints E, F and G, and to be honest, there are quite a lot of reasonable ways to approach this. So I'm just going to show one possible way to deal with this problem. As we have already seen on a couple of occasions, when we have a quadrilateral and we want to find the area, it makes sense to split it up. So to make use of the midpoints, I'm going to split up along the diagonal AF. Now in this case, I think it is slightly better than the diagonal EG, although it wouldn't be wrong to split via EG, just that with AEF and AFG, you are more easily able to say that it has an equal area to another triangle. So specifically, since E is the midpoint, we can say that this area are equal, and then since F is the midpoint of EC, this area is also equal. So this is not too bad because it means that if BEC is quite clearly 1/4 of the square, then AEF would be 1/8 of the square. Now notice that I am going with a quarter and an eighth. I don't really want to deal with 64 times 64 unless you are really familiar with powers of 2, in which case these would be very straightforward. But otherwise, I think we can deal with the fractions more easily and then just multiply by the total area once we are done. Now if we were to come back and look at AFG, AFG is equals to AGD, and in fact, if we want to find AFD, we realize that ABF and DCF are actually symmetric because F is the midpoint, so this would be along the line of symmetry. So I can actually kind of indicate a couple more. I'll just draw it like this to make it clearer that these are all equal as well. So each of these dots is 1/8 of the square, each of the blue dots I should say. And so that means that AFD is 3/8 of the square and AFG is 3/16 of the square. guess you can appreciate that this is an easier thing to deal with compared to an area of 4096, an area of 2048, an area of 1024 being filled up all over your diagram. So in total, you have 1/8 plus 3/16 multiplied by the total area, which is 64 squared. So 5/16 times 64 would be 20 times 64 equals to 1280. So when they give us a square, the idea of using symmetry is really useful because we can kind of make intuitive guesses which are quite easy to verify. Because when stuff look equal, they probably are really equal when you're in a square. Whereas if the question mentioned any triangle and you make your triangle look really equilateral or really right angled, you may be making an assumption that isn't actually right. So that's the reason why when we have a square, this sort of approach works very well. We just mark up many things that are equal to each other. Alright, question 19, I would say is one of the more challenging problems at the SMO junior level. So x is the integer that consists of all the integers from 1 to 81 written from left to right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, then 1, 0, 1, 1, 1, 2, 1, 3, and so on. What is the remainder of x when divided by 2020? Now 2020 does not have any divisibility test, certainly, and it is quite clear that splitting it up will make things a little better. So 2020, as we have seen in an earlier problem, can be split into 4, which is 2 squared, 5, and 101. The first two, 4 and 5, are relatively straightforward in terms of the test. The remainder when divided by 4 and the remainder when divided by 5 are very obviously 1 and 1 respectively. For 4, we just look at the last two digits, and for 5, we can look at the last digit. Now this leaves us with the question of dividing by 101. What is the remainder when x is divided by 101? Now the idea here actually extends the divisibility test for 11 to 101. And we'll need to use a little bit of modulo arithmetic to solve this problem. Now the idea of modulo arithmetic is that you can focus on a single number that you're dividing by. In this case, 101. If the question only asks you for the last digit, you can say that we are doing our operations modulo 10 because the last digit is just the remainder when divided by 10. And what modulo arithmetic allows us to do, roughly speaking, is that if we are doing modulo 10, you can just focus on the last digit. If we are doing modulo 101, we can add or subtract multiples of 101 freely in any part of our calculation. And let me show you how that applies in this example. And then you can look back at the easier divisibility test for 11 and see whether you can figure out why it works. Now, how I'm going to do this is I'm going to split it up into blocks of 2 digits. So it's going to look like 81 and then 80, a lot of 2-digit numbers until 10, and then 9, 8, 7, 6, 5, 4, 3, 2, and then 1 at the front. Now I'm going to split this up like this, and then I'm going to write it in a rather unusual looking way that maybe looks a little counterproductive. So I'll say x equals to 81 plus 80 times 10 squared plus 79 times 10 to the 4 plus 78 times 10 to the 6. So it's like place values, except that now I'm taking the digits 2 at a time. And so on until 10. 10 would be going back 71 steps. So it would be 10 to the power of 2 times 71. And then after that, it would be 89 to the power of 2 times 72. 89 followed by 67. Sorry, that shouldn't be a plus, that should be a times. So let me correct that. Plus 45 times 10 to the 2 times 74. Plus 23 times 10 to the 2 times 75. Plus 1 times 10 to the 2 times 76. And we can sigh and take a huge breath of relief. That sounded wrong. I think we mean breathe a huge sigh of relief. But really, all of these numbers, I have not multiplied them because they don't actually matter that much. And here's why. We notice that 10 squared is 100. And so when we are doing things modulo 101, it means that we can add or subtract any multiple of 101. And that includes subtracting off 101 from 100 to make it -1. And we write it like this. So 100 is equivalent or congruent to -1 modulo 101. Now when we do this, what it means is that we are going to change the number in terms of 100 and -1 are obviously not the same number, but the remainder when divided by 101 is the same, i.e. the difference is still a multiple of 101. So let me show how this would work. Every time we see 10 squared, we can replace it by -1. So it will be 81 minus 80. 10 to the 4 is 100 squared, so it is now -1 squared. So plus 79. Now 10 to the 6 is 100 cubed, so it is -78. And you see that the signs alternate plus, minus, and so on, which is really similar to how the test for 11 works. Now we get to here, the last one would be 100, which is -1 to the power of something odd. So that means that it will be -10, then plus 89 minus 67, plus 45, minus 23, and then plus 1. Now if I were to just be a little bit messy in how I wrote it, what it means really is that you erase all of these and just replace them. And let me just replace the first few. 100 has become -1. 100 squared has become -1 squared. 100 cubed has become -1 cubed, and so on, until the last one has become -1 to the 76. This is really what has happened. And all of these are pretty straightforward to calculate now, because it is going to be 81 minus 80, 79 minus 78, and each of these differences are 1. So the first part of this, there are 72 numbers and every pair gives you 1. So 36, and then we calculate these. The pairs are 22 and 22. Finally plus 1, and this is 81 modulo 101. Now since I overwrote some of the things I was writing, I should use congruent instead of equal. So 81 modulo 101, and this now comes back to our original problem. How do I put these back together again? Now the fact that I can put these back together again is not something we can take for granted. But it is true using the Chinese remainder theorem. Now the Chinese remainder theorem doesn't actually tell us how to do it per se, it just tells us we can. So the Chinese remainder theorem kind of says okay. It doesn't tell us what to do, it tells us that this method works. And so because we know it works, we can actually try to learn how to handle this in general. How do I put them back together again? Now this is not the best example to illustrate the Chinese remainder theorem because it works immediately. But the idea is that you start with the biggest prime factor or prime power and you look at the remainder and then you try to adjust it until it satisfies the rest. So for example, if it was not 1 here, but it were 2, then I would look at 81 modulo 101 and say that does not satisfy this. But if I add another 101, then 182 does satisfy this. So I would use 182 to satisfy these two, and then I will continue adding on 5 times 101, which is 505, until it satisfies the first condition. But this problem is not so difficult because at least, despite the little bit of gymnastics we had to do with modular arithmetic, 81 is already 1 modulo 5 and 1 modulo 4. And so that means that your answer is just 81 itself. So as mentioned, this is probably the most difficult question because you need to really understand how modular arithmetic gives you your divisibility test and not just remember them superficially. So I would encourage you to think about how the test works for 11, and perhaps after you manage to figure it out, this would make even more sense than it currently does. Now, finally, we move on to question 20, which is actually far easier than all the rest if you have already seen the approach for how we convert recurring decimals to fractions. So in this problem, A is 1 over 7 times 3.1415151515, which is kind of meant to remind you of pi, but really has nothing to do with pi whatsoever. So 3.14151515, so on. Let's plug this out and go over the approach that we use to convert recurring decimals to fractions. Now, to be fair, this is technically a geometric series, and so recurring decimals are just special cases of geometric series. However, for the SMO Junior, understanding geometric series in general is not required, so we just need to understand it for this specific example. So what we do for recurring decimals is you look at the length of the repeating unit. In this case, the repeating unit is 15, so it has length 2. So then you want to shift the decimal point by 2 steps. And so how we do that is you write 100x is 314.15151515 and so on. So really, I've just shifted the decimal point 2 steps to the right. But because 151515 is repeating, if I take the difference, 99x would be equal to 311.01, and there's nothing behind because everything in the 151515 repeating block here will cancel out. So 99x equals to 311.01. I could probably multiply it by 100 first. And then there is a common factor of 3 which I can cancel out. So x is 10367 over 3300. Now the question, slightly annoyingly, has also included a 1 over 7 over there, possibly to further confuse a student to think it has something to do with pi. But it doesn't really have anything to do with pi, we just need to put this back in and multiply it by 1 over 7. 10367 is actually divisible by 7. It is equal to 1481, and this would be our final fraction. So 1481 over 3300, and so the answer is 4781. Now this brings us to the end of the 4th video, and in our final video we will go through the last 5 problems of this SMO Junior 2020.